Hello. So far, when we've talked about inequalities, we've discussed single and hopefully simple inequalities. For instance, here we had one equality symbol. We solved it through, and we saw that x is less than 1. And then we can go ahead and plot that if we wanted to. Here's a number line, here's the number 1, less than, we have an open circle because we're not really including it, and then the numbers that are less than 1. So we point in the negative direction because those are the numbers that are less than 1. And we also made notes in the previous video, which I highly encourage everyone to check out, why exactly when you divide by a negative number, or if you really multiply by a negative number, same difference, you flip the sign or the direction of the inequality. From here, initially we said greater than is versus less than. Here now we have x is less than 1 or 1 is greater than x. Why does that flip? Well, we answered that in a previous video. However, today I want to extend our focus here. Not by too much, but enough to really add some nuance. And we're going to do this with something called compound inequalities. Equalities. So, as you may have noticed, when it comes to simple inequalities, when we have something like x is greater than 1, we have a lot of numbers that are greater than 1. An infinite number of numbers. For instance, 2, 3, 3.1, 3.11, 3.111111. You can keep going like that for as long as you want. However, what we noted is that we can kind of represent that by a line of numbers starting at 1 and on. But what if we wanted to have some extra solutions here? What if, for instance, on the number line, what if we also wanted, for reasons unbeknownst to us, we wanted the numbers that are also less than or equal to 0? What if we only really wanted to leave out these numbers here between 0 and 1, not including 0? Well, we would need a second equality or inequality. In the first little compound inequality type we're going to have, it's what we call the or inequality. For instance, we will say x is greater than 1 or x is less than or equal to 0. And this matches our graph. There's no fancy way to write one single inequality that's going to give us both of these solution sets. However, if I were to write the word or here, and this is like an inclusive or, we could say, okay, we want x to be anything that is either greater than 1 or less than or equal to 0. All of the numbers on both of these segments, these rays, would work. All right. Now, when it comes to solving something like this, you almost always see when we're trying to include both the word or. For instance, if I were to write 2x plus 4 equals 8, I'm going to change that from equals to be, let's say, greater than. So, and then I have negative 2x plus 4 is greater than 8. Now, of course, these look deceptively similar. However, if we solve them through, we see that we have 2x is greater than 4, and so x is greater than 2. And then here, on this inequality, we'd have negative 2x is greater than 4. However, we'd have x is less than negative 2. Again, remember the symbols will swap, and when we divide by a negative, here we divide by negative 2. And then we have this expression here, less than negative 2. If I were to then graph these, we'd wind up with negative 2, positive 2, stuff that is greater than 2, stuff that is less than negative 2. The potential values of x can either be or greater than 2 or less than negative 2. And so this is what we call or inequalities, or a compound inequality where we're considering either of the solutions. The other type of inequality we can have is the and inequality, and the pair of inequalities where we consider the and relationship. Now for this example, it's going to be hard to see exactly what I mean by the and, because there's actually going to be no values that work. So the and symbol, sure, idea, perhaps, is where we have the values of x, where it's true that x is both greater than 2 and less than negative 2. Well, you check out our graph, here are all the numbers that are greater than 2, and over here we have the numbers that are less than negative 2. There's no overlap. And so, for instance, we could say there's no numbers, or like this is called like the empty set, the thing that's empty. There's no numbers that would be suitable for x such that both of these are true. And so and is looking for when both inequalities that you're given, or more than 2 perhaps even, are true. Now let's go ahead and consider a different example. Let's imagine here that we had less than, let's see, 12 maybe, and we'll make this a positive. So I'm going to leave the left side alone, or the left expression alone, and now I'm going to resolve the one on the right. So here I have 2x is less than 8, x is less than 4. Let's first consider the case where we have an or inequality. I can draw my graph. I have, for instance, the numbers 2 and 4, because that's what I solved for. Might as well use those. Well, here we have that x is greater than 2. So we have all these numbers. And then we have x is less than 4. So we have all of these numbers. And as you may notice, we have all numbers included here. Sometimes you might see this written as this guy, which stands for all real numbers, because, well, we're hitting all real numbers. Anything that's less than 4, anything that's greater than 2, we consider as being met here. However, there's another idea that we can test here, and that is the and inequality. And here we will have actual solutions. So I'm going to look at this graph again, and I'm going to use this light blue color. I'm going to say, okay, for what values of x is this inequality true? And at the exact same time, is this inequality true? Well, hopefully you notice, that's the case when we are in this little overlapped area here. Because over here, x is not greater than 2. Over here, x is not less than 4. But right smack in the middle, where I highlighted here, this guy absolutely is. And so, to kind of decrease the clutter here, I can imagine, instead of writing all that, we can just simply put in a graph of the numbers that work. Because look, these are the numbers that are precisely less than 4 or greater than 2. And of course, we use open circle still because we're not including either of those numbers. Because, for instance, 4 is not less than 4, and then 2 is not greater than 2. So we still have the open circles, but now we have this little chunk between. All right. And